Okay, hey, welcome back everybody and welcome to our online students. Today what we're going to do is we're going to take a look at bond length and bond strength and then something called polarity, which is to say the unequal sharing of electrons in a chemical bond. Now to get us started here, the bond length depends on what atoms we're talking about. Some atoms are bigger than others. So if you were asked for some reason, hey, Emma, you're here today. Woohoo, good to see you. What's the biggest, fattest element on the periodic table? Francium, right? And so we would expect that if francium was bonded with another atom, that bond length would be fairly large. And if we wanted to find an element that was really, really small, a really small element, yeah, helium. Helium would be a small element, and if it formed bonds, helium tends not to too much because it's a noble gas, but if it did, that bond length would be fairly small. So it does make a difference which elements they are, right? Some are bigger than are others. Okay, and it also makes a difference on the number of bonds. The more bonds you have, it turns out the smaller that bond length is going to be. And so we have something called a bond order. And that bond order is some kind of a measure. Why is there no chalk? Ah, here we are, chalk. The bond order is counting the number of bonds covalently shared between two elements. So for example, if we have this molecule right here, we call this water, and you cannot pass this class if you can't draw that. It's like Avogadro's number. You shall not pass. Got to know this one. All right, so here's water. And if we wanted to know what is the bond order, the bond order is the number of bonds between two elements. And so the bond order here would be equal to 1. The bond order is 1. There's one covalent bond here on average between the hydrogen and the oxygen. That's fairly easy. But if we were to take a look at ozone, for example, and the last time we got together, we took a look at this molecule here. Oh, good thing I don't get paid to draw. Okay, looks something like this. And here, throw in some lone pairs. Okay, like that. And then with this one, we would say that our bond order is Sean Connery, right? Starts with Sean Connery and then goes to, who is the next Bond? Daniel Craig. No, he's like the latest one. There's like a whole bunch of, Roger Moore. Yep, there's Roger Moore. Now, there was a guy who just did one movie, kind of gets missed in the big scheme of things. Yeah, and some of you are like, what the hell is he talking about? Chemistry, James Bond. Okay, so the bond order here. If we took a look at the bond order here, and you might say is equal to 2 because it looks like that's a double bond, but that would not be right. And you say, oh, that's a trick question. It must be 1 because there's 1. No, and that would be wrong too. So what's the bond order? 1.5. Excellent. 1.5 because this is a resonance structure, and we say that this double bond goes back and forth. Goes back and forth. So on average, we have 1.5 bonds is our bond order. Now in your textbook, there's this whole table, and this table shows us the bond length in picometers, and then it also shows us the bond energy, kilojoules per mole. And this is the amount of energy it would take to pull these atoms apart from each other. And there's all kinds of numbers, and there's all kinds of bonds there, all kinds of stuff there. And students say, do I need to memorize this, Professor Locken? No, don't memorize this. Did you have a question? Ah, okay. All right. So, but let's make an observation here. Find in the upper left-hand corner, we have carbon-carbon bonds. Carbon-carbon bonds. Okay, see those carbon-carbon bonds there in the upper left-hand corner. See if you can't find some sort of relationship there. Look for a relationship. I'm going to go carbon, 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 carbon. Okay. All right. Emma, you picked somebody here last time we got together, and they're not here. It's getting knee surgery. Okay. I don't know. Is that acceptable? I think so. Yeah, we'll probably let that one go. Can you help me out? Thank you. How are your knees? They're good? You want to trade? Okay. So help me out here. When we look at the bonds up there, carbon-carbon, single, double, triple, do you notice any kind of a trend there? So as the number of bonds increases, the length decreases. Yeah, I like that. Okay, so here's what I'm going to do. I'm going to go, let's see, number of bonds, and then bond length. Bond length, right? Because like Sean Connery, I think, is 7 films, and then Timothy Dalton was 2, and then Daniel Craig, I think he committed to 4 now. That's the bond length. No, it's not. Okay, so you pointed out that the number of bonds, 1, 2, 3, as the number of bonds increases, the bond length decreases. So I'm going to go down, and I'm going to go up like this, and then like this. Okay, so if we have more bonds, the bond length gets smaller. Now, the way that I visualize, what does your mom call you? Carter. Okay, thank you, Carter. All right, so Carter, thank you for helping me out with this here. So I made the mistake of asking somebody, what does your dad call you? And says, I thought my name was Jesus Christ, because every time my dad called me, it'd be Jesus Christ, right? So now I ask moms. Moms are usually nice. Well, okay, I'm generalizing. Okay, thank you, Carter. The way I visualize this is like rubber bands. If you have 3 rubber bands, it's going to pull them closer together and be harder to pull them apart. So I'm going to put here bond energy. Bond energy. That's the amount of energy it takes to pull them apart. And so if we have 3 bonds here, a triple bond order is 3, that's a lot of energy. 1 bond is less energy. Okay, so that's kind of the trend. Think like rubber bands. 3 rubber bands are going to pull it really close together and be hard to break them apart. All right, Carter, you're never going to forget this. Never going to forget this. So we don't need to memorize this table to be able to answer a question like this. Which is the weakest bond? Carter, can you help me find somebody? I need somebody to help me answer this question. Kevin. Where's Kevin? Hey, Kevin. Glad you're here today. Kevin, help me out. It says, what's the weakest covalent bond? Don't say Timothy Dalton. Pardon me? A. A is the weakest bond because it's going to take the least amount of energy to pull apart. Now, did you memorize this table? Yeah? You're just like that. That's awesome. Okay, nicely done. Nicely done. All right, so now bond order is the number of bonds on average, and so for ozone, we say that this is a resonance structure. That bond flip-flops back and forth, and so we have a bond order of 1.5. 1.5. Okay. Now, taking a look then, we're going to switch gears here a little bit and take a look at polarity of bonds, and that is to say the unequal sharing of electrons. Unequal sharing of electrons. Now, we have some bonds that we say are polar, and that is to say we have an unequal sharing of electrons. And so when I take a look here at I'm looking for colored chalk. Here we go. If I take a look at my water molecule here, my oxygen is a little bit electronegative, hydrogens are electropositive, like this. And that is to say the electrons are drawn or pulled towards the oxygen atom. And so we might think of this as having a higher electron density towards the oxygen than the hydrogens. Makes us a polar bond, Now, polar covalent bond, it says polar covalent bond here, it's just unequal sharing. They're still sharing electrons, it's just the oxygen just shares a little bit more, or we say it's just a little bit more greedy. The electrons spend more time there. And polarity just means that it's unequal. It's a little bit positive and a little bit negative. And we have a fancy term for that that's called a dipole. Dipole just means that we have di as two poles, like north-south, positive, negative. Dipole, just fancy terms. And then we have nonpolar covalent bonds. And nonpolar covalent bonds is when the bonds, or the electrons, are being shared relatively equally. Now I'm going to show you a graph here. This is also from our table from your textbook. Is going to show you these here. All right, so here we have three different molecules on the right-hand side. The top one is chlorine. And chlorine, we have Cl and Cl. And it tells us there that this is nonpolar covalent. Nonpolar covalent. So that means equal sharing of electrons. And how would we know just by looking at this that it's equal? Well, Kevin, you answered the last question so well. Could you help me find somebody to help me with this one? Grace, we're going back and forth. Grace? Grace, thank you for being here. Okay, so Grace, I'm looking at this and I'm scratching my head saying, how do I know that these are sharing equally? Any thoughts on that? Okay, so Grace, what you're saying is they're equal. They're the same, right? And if you look on the periodic table, they both occupy the same spot on the periodic table, chlorine, right? I picture this like if you had a tug of war between siblings and they're twins, theoretically it should end in a tie, right? Because they're twins, theoretically. They should be the same in a tug of war. Now let's compare that to something a little bit different. So for example, we have HCl, like this. Here's HCl, and this is polar covalent. Covalent. Okay, polar covalent. So polar covalent, we can look at this, we can say, oh, these aren't twins, they're different. They occupy different places on the periodic table. There should be some difference between who's going to win in this tug of war. So this is going to be polar covalent, okay? So unequal sharing of electrons. And then the last one there is NaCl. NaCl. And this one is not, it's not nonpolar, and it's not polar, it's ionic. And say, well, that's different. How do I know that this is ionic? Grace. Could you help me find somebody to answer this question here? Abby, help me out here. Polar covalent, nonpolar covalent. This one's not either. It's neither of those. How would I know that this is ionic just by looking at it? They don't share electrons, right? You are correct. They don't share electrons. Don't share electrons, right? Like that brother or sister that doesn't share their Legos, okay? So how would we know that they don't share? Just by looking at it. I don't have a bond there, that's true. Metal and non-metal. It's a metal and a non-metal, right? So metals and non-metals make ionic compounds, whereas these here are nonmetals, and so they make covalent compounds. Okay, nicely done. Thank you. Okay. Now, somebody came up with a whole table where they plug these numbers in for electronegativity. Now, these numbers, you don't need to memorize these, But the idea is, let me show you the table. I'm just going to show you the table here. Okay, so here's the table. And this is, okay, stupid story for you. Have you ever heard that vitamin C is like good for you, and if you have lots of vitamin C, you don't get colds? You ever heard of that? Person who came up with that was this guy named Linus Pauling. He was a chemist. Turns out we don't know if that's really true. But he got a Nobel Prize in chemistry, so everybody just kind of believed, well, he's got to be right about the vitamin C thing because he's right about other stuff, right? Which isn't always true. So anyway, so Pauling came up with this table here of electronegativities, and it just has values like between 0 and 4. And you can see fluorine up there has got a value of 4, and then francium is down here at 0.7. And the idea is which elements like or want electrons the most. So fluorine at the upper right-hand corner really, really wants electrons, like gobbles them up. And then francium down here, big fat francium, meh, not so much. Okay? Now, can you see a trend in this? You see a trend, right? Like if you're going to draw a periodic table, you could say that our electronegativity, if I were to draw a periodic table that looks something like this, okay, periodic table, and then I were to write electronegativity tends to go this way and this way on our periodic table. It also tends to go, you notice that we have small elements here, we have big elements here. Small elements, the electrons are close to the nucleus, and therefore we have a stronger pull on those electrons. So electronegativity tends to go in that direction there. All right, so we're not going to memorize. Don't memorize this. I did have a student memorize this once, and like on a test, and he's like, oh, this element is this, and this element is this. And then he goes back here to this slide here, and he did the math like this. And it says, oh, well, if the difference is greater than 2.0, the difference in those electronegativities, then it must be ionic. So I was like, good God, why did you memorize that? It's a metal and a non-metal. But good for you. I am impressed. Okay, so let's try this. This is a great test type question. It says, which of the following bonds in each pair are more polar? Which ones are more polar? I need your help. Can you help me find somebody to answer this question? Somebody to help me with this. Isaac. Carbon and sulfur or carbon and oxygen. Carbon and sulfur, carbon and oxygen. Which one is going to be more polar? Which one will be more polar? Isaac. Carbon and oxygen. Okay, you made a prediction. Carbon and oxygen. Help me through. How did you figure this out? I'm going to look at a periodic table here. You said carbon and oxygen versus carbon and sulfur. Because oxygen is higher up. Yep. And it's more this way. It's more this way than is sulfur. Okay. Yeah, nicely done. So you'd be correct. And did you memorize this, Isaac? No, you don't have to. Okay, nice. Okay. Can you? I need another person here. Tabitha. Okay, Tabitha, help me out with the middle one there. I've got chlorine and I've got oxygen there. Chlorine gas, oxygen gas. Which one's going to be more polar? The two oxygens? And if you had to guess again, and if that wasn't right, trick question. They're the same. They are the same, yeah. They are the same. Are these ones polar or nonpolar? They're nonpolar. Tabitha, how would you know that? Because they're the same elements. Twinsies, right? Twinsies. So the tug of war is going to end up in a tie. Nice. Okay, Tabitha, I need one more person to help me out with that last one there. Sam. Woohoo, Sam. Sam, help us out here. I've got nitrogen, hydrogen, and carbon and hydrogen. which one of those, Sam, would you feel would be a more polar bond? Nitrogen and hydrogen. Okay, and why would you say that? Nitrogen is further apart from hydrogen, so a greater distance between the two. Yep, so if I go back like this, a greater delta, a bigger distance between those two. Okay, so it should be the nitrogen, hydrogen, because nitrogen and hydrogen are further apart than carbon and hydrogen. Sam? Yes, yes, okay. Yes, thank you very much. Oh, you are amazing. Thank you so much. Okay, so any questions on that? I don't want people to memorize this, because if we understand the trends, then we don't have to memorize this. And that's my goal. I really hate memorizing stuff if I can avoid it. Except for like your wife's birthday and when you got married. Those are things to write down, right? You got to remember those things. Okay. It was easy. We got engaged on Valentine's Day. Oh, yeah. Then we got married 6 months later. Oh, yeah. So stupid story for you. On our first date, we decided we were going to get married. What? Yeah. I don't know. I married up, and I was not going to let this go. All right. Okay, so any other questions? Hey, Isaac, the very first one up there, we've got CS. That's copper and sulfur. And then we've got copper carbon. What am I thinking? Man, it's a good thing I don't get paid to know chemistry.